In a previous video, we talked about two operations we can do on vectors, namely scalar multiplication and addition. In this video, we're going to look at the geometry of these operations. So first, let's consider the geometry of scalar multiplication. Here we've got a vector u in R2, drawn sort of in its standard position. This in particular is the vector 1, 2. So we could, write that out if we'd like. We could consider kind of the arithmetic and the algebra of doing these operations. I want to mostly focus on the geometry, but if you want to kind of double check what you would get in each of these cases algebraically, you certainly can. So first, let's consider the vector 2u. So multiplying the vector u by the scalar 2, you could do that using the formula we had earlier. You'd get the vector 2, 4. Let's take a look at that vector here. So here's the vector 2u. Again, it's the vector 2, 4. But what I want to kind of focus on is what it looks like on this graph compared to the vector u. So if we are kind of looking at 2u compared to u, we can notice hopefully that it is moving in the exact same direction as u, but it is exactly twice the length of u. So when we multiply a vector by a scalar multiple, geometrically, we are literally scaling that vector by that particular scalar multiple and not changing the direction. So when it comes to kind of the geometry of vectors, the two things we care about are the direction and the length. And in the case of scalar multiplication, we are not changing the direction if the scalar is a positive number, but we are changing the length by the amount of whatever that vector, whatever that scalar is. So in this case, 2u is in the same direction as u, but twice the length. Similarly, 3u is in the same direction as u, but 3 times the length. If we consider a negative scalar multiple, so here we have the vector negative u, then we are not going in the exact same direction. In fact, we're going in the exact opposite direction. In the case of negative u, we're going to be moving in the opposite direction of u, but not changing the length. Negative 2u, we're doubling the length and moving in the exact opposite direction. And negative 3u, we are tripling the length and moving in the exact opposite direction. So all of these sort of land on the same line out of the origin, but we've got these different lengths. If our scalar is 0, then 0u gives us the vector 0, 0 in this case. That is what's known as the 0 vector. So if we were to sort of write that out, we'd use our vector notation, either with bold font or with this arrow notation. In R2, the 0 vector is, again, this two-dimensional vector, 0, 0. When we're sketching that vector, we would literally just draw a point at the origin. It does not have a length or a direction, but it is an important vector. It does play an important role, and it is technically a scalar multiple of the vector u, since we can take u and multiply it by the scalar 0 to get the 0 vector. So something just to keep in mind moving forward in the course. Moving on to visualizing vector addition, here we've got two vectors u and v. Again, we are going to mostly be focusing on the geometry here, but if you wanted to do the arithmetic to confirm what we get with these different operations, you certainly could. The vector u appears to be the vector 3, 1, and v appears to be the vector negative 1, 1. If we looked at u plus v, if we did the arithmetic, we'd get the vector 2, 2, and here it is drawn. And it doesn't kind of, on its surface, I think, appear to be too connected with u and v immediately, but if we were to draw in this parallelogram here, then we can see maybe a connection starting to form. How did we create this parallelogram? Well, we've got the vector v, so we can sort of focus on first moving along the vector v, and then we can kind of complete the top side, if you will, of that parallelogram by adding in the vector u. And so the line over here is essentially the vector u, but instead of coming out of the origin, it is going to be coming out of the end of vector v. We could kind of consider this in the other direction as well, first traveling along the vector u, and then when we start at the end of u, we travel in the direction of and length of v. So we've got these vectors u and v, and we can build this parallelogram. So this is the vector v over here. This is the vector u up here. And so u plus v can be built by kind of doing two things. For doing it in two different ways. First, traveling along the vector u, and then traveling along the vector v to get up to u plus v. Or we could first travel along the vector v, and then travel along the vector u, and end up in that same place. So we can visualize u plus v as, again, sort of being this connection of the vectors u and v, or as the diagonal of this parallelogram that we've drawn, where the sides are, u and v each drawn twice, first coming out of the origin and then each coming out of sort of the end point of the other one to build this parallelogram to get us, this parallelogram where one of the diagonals is u plus v. Another thing we might want to consider is u minus v. So again, if you do the arithmetic, you would find the vector u minus v in this case would be the vector 4, 0. But visualizing this geometrically, one way we can think of this is by, instead of thinking of it as u minus v, we think of it as u plus negative v. And so if we think about vector addition in the way we just did earlier, we can kind of think about traveling along the vector u, and then at the end point of it, traveling the negative direction, or the sort of distance of v, but in the exact opposite, in the negative direction. So we have our vector u, and then we have our vector, minus v that we're kind of combining here. So here's u, here's the vector minus v, and those come together to give us the vector u minus v. Another way we can visualize this, if we shift it, so instead of starting at the origin, it starts at the end point of v, then build that same parallelogram we had before. There's u plus v, and what we can see is actually u minus v forms the other diagonal of that parallelogram. So that parallelogram, is kind of an interesting thing. It gives us both u plus v and u minus v as the two diagonals. This is something that we'll continue to explore as we move further in the course. Next, let's just look at sort of a general kind of combination of both scalar multiplication and addition. So here we've got the vectors u and v again, and drawn in is 2u minus 3v, which you could compute again using the formulas. You'd end up with the vector 9, negative 1. How could we have visualized this geometrically? Again, what we can do is kind of just build this up. So 2u would be, taking the vector u and just sort of doubling its length. So here would be the vector, I guess 2u. And then we would take v and kind of go in the negative direction of v. We could start that at the end point of u, and then we'd add sort of, the negative direction of v and 3 times it. So we've got here, this whole big thing here would be the vector 2u, and this whole thing here is the vector negative 3v. And so hopefully you can see the connection between the vector u and 2u and the vector v and negative 3v, and then adding those two things together to get the vector 2u minus 3v. Next thing I want to look at is kind of doing a bunch of combinations. I want to look at, so this is again the vector u plus v that's drawn in there. I want to, and what we'll see in the next few slides is look at u plus some multiple of v. So u plus 1 times v is what we're seeing here. Next is u plus 2 times v. So this is u plus 2 times v. This is u plus 3 times v. U plus 4 times v. And then u plus 5 times v. Here's u minus v, u minus 2v, u minus 3v, u minus 4v, and u minus 5v. So we've got all of these vectors. Again, all of these are of the form u plus some scalar, maybe I'll call that k, times v. And what I want us to notice here is that actually if we draw all these in their kind of standard position, starting at the origin, then if we connected all those endpoints, we would get a straight line. So something interesting there. What is that line? It's the line where if we kind of started at the origin and traveled out a distance of u, which would get us to this point right here, and then kind of moved in the direction of v by any kind of scalar amount. So positive values getting us up there, negative values getting us down there. So that line, in a sense, is all the points on that line can be gotten by considering vectors of the form u plus k times v.